Hey guys, you made it to your last set of notes for Unit 2. Notes D is all about periodic trends, and then we'll go over some periodic groups. So first, to start with the trends, there are four that we're going to look at: the atomic radius, ionization energy, the radius of the ions formed, and then something called electronegativity. So let's get started. The atomic radius is basically how big an atom is. It's measured by radius because typically it's found by going halfway between a bond between some atoms. But basically it's giving you the size. So as you go down a group, the atomic radii is going to get bigger, and as you go across from left to right, it'll get smaller. So you can kind of see the trend in this section of the periodic table that's pictured here. As you go down the group, you're going to be adding energy levels. You're going to have more energy levels added as you go down. So for example, hydrogen in the first energy level only has one energy level. Remember, its electron configuration was just 1s. Whereas if you go down to like potassium, now you're in the 4s area. You've got 4 different energy levels. Energy levels are literally defined as the distance of the nucleus. So further away would have more energy levels. So of course they're going to get bigger as you go down the group. But there's also something else at play. The shielding effect basically occurs from the core electrons. So say this is the nucleus, and I have some energy levels, some electrons on here. The electron that's on the outer level would have some interference because there's also electrons on this inner level. These electrons act as a shield, blocking what would be an attraction between the electron and the nucleus. These other electrons get in the way of that, so we call that the shield. So it is literally further away, and there's interference in the attraction. So why is it that it gets smaller as it goes across from left to right? Well, the atomic number is increasing. An increase in the atomic number means an increase in the protons. So you're going to get more of a nuclear pull as you go across the period. Which would be bigger, sodium or potassium? These are on top of each other on the periodic table. Potassium has more energy levels and more blocking from the core electrons, so it would be bigger. What's bigger, phosphorus or chloride? These are right next to each other on the periodic table. Phosphorus has less protons, and so it would have less pull holding it closer, so it would be bigger. What's responsible for the shielding effect? Meaning, what causes it? What is the problem? That would be the repulsion of the other electrons. What does the shield interfere with? What is the shield blocking? That would be the attraction between the proton and those outer electrons. So the problem is the inner electrons are repulsive, and their problem that they cause is an interference in the attraction between protons and electrons. Now let's talk ionization energy. Although yes, you can form an ion by either gaining or removing an electron, the ionization energy has to be uniform. So we're going to define it as the energy required to remove the outermost electrons, which means that electrons would rather gain electrons would have a high ionization energy since they don't want to lose theirs. In this graph, we have the ionization energies for each row across the periodic table. For the first row, it peaks at helium, but the second row across peaks at neon. The third row across peaks at argon. Are we noticing a pattern? The fourth row, highest at krypton, highest at xenon, and highest at radon. As you go across a period, the highest ionization energies are those noble gases. The noble gases have the perfect electron configuration, the electron configuration that all other atoms on the periodic table are jealous of. So of course they don't want to lose their electrons, and they would have the highest ionization energy. As you go down the group, it becomes easier and easier to remove an electron because those electrons are further and further away. When they're easy to remove, that means that takes a low amount of energy to remove it. So the ionization energy would decrease because it's easier to remove. Now, why is it easier to remove? Higher energy levels, meaning increased distance from the nucleus. So the further away that electron is, the easier it is to remove. And then just like last time, we also have these inner electrons that would create a shield. So you have the shielding effect and the distance from the nucleus always being a problem as you're going up and down a group. So for ionization energy, that's going to cause it to decrease. As you go across a period, the factor is always the pull from the nucleus. So as you go across the period, the atomic number is increasing, which means the pull on the electrons is increasing. So it's going to be harder to remove an electron if it's being more strongly held by the nucleus. What is ionization energy defined as? The energy to do what to an electron? To remove it. So now let's look at sodium, potassium again for ionization energy. Again, they're right on top of each other in group 1. Which would have a higher ionization energy? That would be sodium. Sodium only has 3 energy levels. It's going to be closer to the nucleus with less shielding. Now let's look at phosphorus and chloride, which are on the same group, but chloride has more protons. Which is going to have a higher ionization energy? Chlorine, the one with more protons. Now let's look at ionic radii. What does becoming an ion do to the radius or size of an atom? There is so much important information on this slide. Let's start with cations will come from metal atoms, and anions would come from non-metal atoms. Cations with the metal atoms are always going to come on the left side of the periodic table. They only have maybe 1, 2, or 3 valence electrons, so for them it would be easier to give up electrons in order to bond. That means metal atoms will always become positive. Now let's look at ions that form from nonmetals. Nonmetals are on the right side of the periodic table, which means they have maybe 6 or 7, maybe 5, 6, or 7 valence electrons. So for them it would be easier to gain an electron, making them more negative, or therefore an anion. So cations always lose electrons, which is why they become positive, and anions always gain electrons, which is why they become negative. So then gaining electrons always happens on the right of the periodic table from the nonmetals, and the losing electrons always happens on the left of the periodic table from the metal atoms. Now let's talk size, starting with the cations. Cations, let's say, have layers, or let's pick an example where we have layers of electrons, and now we want to lose electrons. So let's say I only have 1 electron on my outermost shell. I'm going to lose that electron. That's what bonding is all about. We'll get into that in Unit 3. So when we lose that electron, I'm going to lose that entire shell. Does that look bigger or smaller to you? Of course it's smaller. Losing an energy level will make the atom smaller. Now let's look at this from an anion's perspective. Anions are always going to be larger. Not because they're gaining another shell, so it's not as dramatic and exciting, but if I have a few electrons on my outermost shell, and then now I'm adding in even more electrons, electrons repel each other. And so you're going to get kind of a swelling of that outer level. They're going to push apart just a little bit more. So anions become larger and cations become smaller. So let's look at a few examples. Let's say oxygen becomes O2-. First of all, would that be a cation or an anion? An anion. And would anions become bigger or smaller? They become bigger. So which is bigger? The anion. Now let's look at sodium. What's going to be bigger, the Na or the Na+? It's going to be the original sodium, because becoming a cation will make it smaller. So with that in mind, what do you think would be bigger, iron 2+ or iron 4+? It would be the 2+. The more electrons it loses, the smaller it'll get. Our last trend is something called electronegativity. So electronegativity is the ability to attract an electron in a bond. So this actually mostly has to do with covalent bonding. So let's say I have atom X and atom Y, and they're supposed to be sharing electrons. So we actually usually draw a covalent bond as a line. So let's let that represent them sharing electrons. Now with a different color, I'm going to show what actually happens. These two little electrons are going to rotate and move around each atom. And if both atoms have exactly the same electronegativity, they would do this evenly. But that's usually not the case. Usually one atom is more electronegative, aka greedy with the electrons. It's going to have a greater pull on the electrons. The electron would stay here more often. As long as it's still going back to visit the other atom sometimes, we would still call that a covalent bond. But the fact that one side gets it more often means that it's unevenly shared. The atom that's more greedy has the higher electronegativity, or ability to attract electrons in a bond. Notice with the trend, it actually doesn't even reach the noble gases. That's because the noble gases do not chemically combine with other elements and therefore would not be considered to have an electronegativity. You can't measure something that doesn't exist. The reasoning behind the electronegativity trend is exactly like the ionization energy trend. As you go down the group, you're going to have more energy levels and more shielding, which basically means that there's a weaker interaction between the nucleus and the valence shell. The bonding would occur in the valence shell, and so if that interaction is compromised, then the atom would be less good at pulling the electrons from another atom towards it. And keep in mind that's what electronegativity is all about, pulling the shared electrons towards an individual atom. Now if that bonded set of electrons is 7 energy levels away with all of that core interaction blocking it, then the atom's not going to be very good at keeping those electrons in its orbit. Instead, the electrons would be attracted to the other atom. As you go across the period, it's all about the nuclear pull. So the atomic number's increasing as you go across, and so that would make the atom better at pulling in bonded electrons. Just keep in mind that by definition, we would stop at column 17, a group known as the halogens. We would not go into group 18, the noble gases, because they don't bond. So it increases across the period up to group 17. So electronegativity describes how much an atom wants to attract electrons or how greedy it is when it does what? It's supposed to be sharing electrons in a bond, known as a covalent bond. Which would have a greater electronegativity or be better at attracting shared electrons, sodium or potassium? Sodium only has 3 energy levels with less interaction in between the valence electrons and the nucleus, so it would have a greater chance at pulling in the shared electrons. What about phosphorus versus chlorine? Chlorine has more protons, so it would be better at attracting the electrons towards it. And why do we exclude the noble gases in all of this? Well, they don't form bonds, and that's kind of part of the definition. So to sum it all up, you have a few key trends and a few key reasons. Starting with the trends. The atomic radius is largest on the bottom left of the periodic table by francium. The ionization energy and the electronegativity is largest at the top right. Ionization energy and electronegativity. Just keep in mind with the electronegativity that you're leaving off the noble gases. It also on here talks about metallic character and non-metallic character. So we'll look at, when we look at the groups where the metals and non-metals are found, you've probably seen this before. There's a stair-step line in here, and the metals are on the left, and the further to the left, this same corner by the francium, the more metallic character, metallic properties you would have, and the closer to the top right, the more non-metallic the atoms would be, the properties of the atoms would be. Now let's talk reasons. As you go up and down, the reason is always that you have greater energy levels and that you have shielding. As you go from side to side, it's all about the protons. So as you go down, you're having more energy levels and more interference from core electrons. So it's going to make the atom bigger, but it's going to make it easier to steal the electrons or lose them in terms of electronegativity or ionization energy. As you go to the right, you're increasing your protons, you're increasing your atomic number. So it's going to make it better at pulling, making it harder to steal the electrons in terms of electronegativity or ionization energy, but it's also going to hold the electrons closer, making it smaller. So know your trends, know your reasonings, and then be able to put 2 and 2 together to answer the test questions. All right, the periodic groups. This next part will go fast. We have a few key groups. You need to know where they are, and you need to know a couple of important properties for each one. Quick recap on some key vocabulary. Periodicity is all about the patterns on the periodic table. Groups go up and down in vertical columns, and periods are the horizontal rows. Here's the breakdown of metals versus nonmetals that I was talking about, and here's my stair-step line. Things that touch the stair-step line are called metalloids or semimetals, meaning they have properties of both metals and nonmetals. If you're on the right of that line, you're a nonmetal. On the left, we have our metals. Notice how many more metals we have than the nonmetals. Here are the locations of the main groups. The first column is the alkali metals, followed by the alkaline earth metals. Then in our D block, that entire central area that's set down in the periodic table, that's all the transition metals. Below that, we have the lanthanides and the actinides, actually called the inner transition metals. And they actually belong in this corner of the transition metals if you follow the atomic numbers. There's not really special names for these few groups. I have heard them called like boron family, carbon family, nitrogen family, and oxygen family, just named after their first elements. They don't have super special names. Column 17, though, is known as the halogens, and there are a few different derivatives name-wise that come off of the name halogen, so that's a good one to know. And then you probably have heard of the noble gases before, because it's a pretty special group all the way at the end. Alkali metals, being the first group, is very reactive. Something you might not know is more metallic character is actually softer. So some people think that metals are supposed to be hard, but you're probably thinking of some jewelry type of metals, which are actually pretty far to the right in terms of metallic character. And a lot of times the hardness actually comes from forming something called an alloy, which is a combination of metals. A pure metal can actually be cut with a butter knife. Like sodium, I have cut with a plastic butter knife before. So metallic character is actually very soft. Group 1 has 1 valence electrons and the halogens have 7. So this idea that they combine readily, the alkali metals with the halogens, is kind of what we're going to get into with bonding. The ideal number would be 8 valence electrons. Since they only have 1 valence electron, they also very easily form ions by losing 1 electron. Group 2 on the periodic table are the alkaline earth metals. Notice the ending here, alkaline earth metals. They're abundant metals in the earth, not on earth, in the earth. Think core, mantle, crust, stuff like that. They're not as reactive because they have to lose 2 valence electrons instead of just 1, so they're going to have higher densities and melting points. The melting point, by the way, is a good indication of the stability of an atom. Next, we have our transition metals, things like iron and zinc. These are things that we take for vitamins, so they're pretty important for living organisms. Now we're going to skip over to our halogens, so group 17. There is a different numbering system that kind of leaves off the transition metals. Since there's only 7 valence electrons, you might see this labeled sometimes as 7A. Basically, you need to know about halogens, that they're super special with their 7 valence electrons being super close to this magic number of 8, that they really like to combine with groups 1 and 2. They form ionic bonds very readily. All the way on the right of the periodic table, we have our noble gases, and this is probably the most well-known group because they're not reactive. All the other elements on the periodic table want to be like the noble gases, and that's actually why they react, is in order to be like the noble gases. The noble gases already have the perfect setup, which makes them non-reactive. The fancy term for that is being inert. And this is the only group that is 100% gases at room temperature, which is kind of a rarer thing. So that's why they're called the noble gases. Now down to our F block, or the inner transition metals. They call them the inner transition metals because they go up here inside of the transition metal area. They're cut out. Remember like how Alaska is cut out of the map. So the inner transition metals are, relatively speaking, fairly far to the left. If we were to draw this out, we'd have our S block, then our F block, then our D block, then our P block. So, relatively speaking, in terms of metallic character, the F block is pretty far to the left. So it's going to be pretty soft. They also tarnish really quickly in the air, but they're pretty resistant to water. So that's kind of where a lot of their usage comes in. And then last but not least, we have our actinide series, which is the second row in the inner transition metals. Most of these elements are actually radioactive, meaning that they have isotopes that have kind of the wrong number of neutrons, and so they tend to decay and produce types of radiation that can be kind of dangerous. So this is our actinide series, all the way at the very bottom on the periodic table. That completes Notes D, and that means that we are done with Unit 2. So the next notes that you would be looking for will be for Unit 3, where we'll explore bonding a little more.